Hi class. This program 4 is going to extend the parser that you wrote in program 3 and turn it into a calculator. It's going to be a nice calculator for real numbers that can do addition, subtraction, multiplication, and division. You remember our original grammar, the one we looked at that was in Backus-Naur form. That's what this BNF stands for. It had these little phrases within the rules with meta-symbols around them. These meta-symbols meant 0 or 1, and these curly braces meant 0 or more. And you remember that in order to see if our grammar satisfied the LL1 requirement so that we could write a recursive descent parser, we had to remove the meta-symbols. We replaced this little piece with F, and this with G, and this one with H, and this one with I. And then we analyzed the grammar to see if our look-ahead sets revealed any problems to us. And of course, the look-ahead sets turned out to be fine, and then we implemented a parser using the new F, G, H, and I non-terminals that we had created during our check. Here was how we did F, for example. Since it was either one AddOp or nothing, we had this rule with no recursion, just F is an AddOp or it's nothing. Since the G phrase was to stand in for 0 or more AddOp terms, we had to add this G out here on the end, add the recursion so that we could get as many of those as we wanted and then kill off the G when we were finished. When we did our look-ahead sets, we found that the look-ahead for this little piece was plus minus, and same for this whole piece right here because it started with, sorry, I'm getting kind of some weird stuff happening here. This whole piece started with an AddOp, so its look-ahead was plus minus. This piece started with a multiply operator, so its look-ahead was either splat or slash, and this one was a digit. Now those look-ahead sets will come in handy when we redo our parser and evaluator, but we're going to go back to the Backus-Naur form and use those look-ahead sets right here in this part of the rule. I'll show you what I mean. This just basically says what I said. We can go back to the Backus-Naur form grammar and implement straight from there and not include F, G, H, and I. The square bracketed phrases, such as we had in expression for the optional plus or minus at the beginning, turns into an if statement if we implement straight from the Backus-Naur form grammar. And our look-ahead set is what we use in the condition of the if. So for example, instead of calling the function f from inside expression, we could just say, at that point where we called f, replace the call to f with this. If current is a plus or current is a minus, then call AddOp. That's what f did. So now what we've done is eliminate the call to f and just put this code right into expression. When you call functions, you get a bit of overhead because the system has to set up the activation record on the runtime stack, and things will just be a little bit faster if we get rid of function calls where we can. Pieces of a rule such as this, where you have curly brace meta-symbols, are going to turn into a while loop because this can be there 0 or more times. The look-ahead set that you found when you did the look-ahead for G will come in handy because that's going to become the condition of your while loop. You're going to say while current is a plus or a minus, then call AddOp, call term. G, remember, accomplished this loop with the addition of a G onto the end of the rule. So it was just a recursive way of doing this that we're now going to be doing iteratively with a loop. And that will actually be more efficient too, because we will avoid the recursive function calls which stack things up on the runtime stack. Now it's all going to be done inside expression. And we're going to do away with G. So here's what we have so far. Remember, this is the rule for expression. There's an optional addition operator at the beginning of the rule. So there might be a plus or minus there, there might not. Then there's a term, and then maybe you have plus another term, minus another term, minus another term, and so forth. Or maybe you have nothing out here. Maybe this term is all you have. Well, here's how the expression is going to be once we have eliminated the call to F and eliminated the call to G. We're going to check for our lookahead here, and instead of calling F, we're going to just do what F did, which is call AddOp. And then here, we're checking our lookahead, but instead of calling G, we're just going to put a while loop that handles this part of the rule. So while the current is a plus or a minus, we're going to call AddOp, call term, and then check again. Do we still have a plus or a minus? That means there's another term coming up. So we call AddOp, we call term, and we check again. And when there are no more addition operators in the string that the user typed, this loop here will quit, and that will be the end of expression. Now, these two calls to AddOp are the only place in our entire program where AddOp gets called. And all AddOp does is match plus or minus. So if you call AddOp, you've already checked to be sure that you have a plus or a minus before you even called AddOp. Then AddOp is going to call match and just update current. So we could be a little bit more efficient here if we just do away with AddOp and put the code that AddOp had in it right here in expression. Like this. Instead of calling AddOp here, just go ahead and call match. You've already confirmed that you have a plus or a minus, so just call match. Pass it current twice, and you know that it's all going to come out in the wash because you've already checked. Now we're gonna this is a little bit misleading here because in the next slide or so I'm gonna undo this. But does it make sense to you that you could do this? I hope so. After we've checked our optional addition operator, then we're going to call term, and then we're going to have our loop, except instead of calling AddOp right here, we're just going to call match. Now, we're not evaluating anything right here. All we've really done is sort of change our parser a little bit, but we're not evaluating. What needs to change if we're going to evaluate? Here's the rule again. So let's think, what is the value of an expression going to be? Well, it's going to be the value of this term for sure, possibly negated. If this is the minus, then it's going to be the negative of this term. Otherwise, it's just going to be this term, because if that's a plus, it doesn't change anything. But then the term's value will have to be modified by the addition or subtraction of any more terms that come along out here. So the value of an expression is the value of this term, possibly negated, plus or minus any more terms that are found in the input expression that the user typed. Now, how do we get the value of an expression? Well, we have to have the value of a term. So we're going to have to rewrite term so that it gives us a value. Actually, we're going to have to rewrite all of our functions, expression, term, factor, and number, so that every single one of them returns the value of the little part of the expression that they parse. Every single one has to evaluate, get a value for their little part of the expression, and then return that to their caller. So let's look at expression. Now this is only about half of it here. I could only fit half on this slide, and anyway it's convenient to talk about it a little bit at a time. The red stuff is what has changed from what we saw just a minute ago. If we're going to evaluate and return a value, we've got to say so right here. We're going to say int instead of void. Now, remember that first term, this term, might have to be negated if this thing turns out to be a minus sign. So here's what we're going to have to do. We're going to have to remember whether that was a minus or not, and we're going to do that with a Boolean variable that's just going to start out being false. So I've called it negative and set it to be false. And then when we call term and it gives us back a value, we're going to have to catch that value in a variable. And so I have declared a variable right here of the same type that the function is returning, and I'm going to use that variable to put the value in as it accumulates, and then at the end I will return it. So here is that first if that handles this addition operator, except we have now added this stuff in red right here that's going to remember if we saw a negative sign. So once we've seen that we do have a plus or a minus, if it's a minus, we're going to set this Boolean variable to be true. And then we're going to match as we were doing just a minute ago. Now when we call term, it's going to give us back a value. We need to catch it. And so we have result gets assigned the value that term gives us back. And then remember, we have to possibly negate that term. And so we look at our Boolean variable, and if it has been set to true, which would have happened right there, then we change result to minus result. Okay, here's the rest of expression. Remember we had a while loop. That part hasn't changed. We're still, for the curly braced portion of the expression rule that said curly brace around AddOp term, we still need this while loop. But now we need to separate out these two cases, the plus and the minus. The reason for that is that if that AddOp is a plus, then we need to add the value of the term onto result. But if it's a minus, we need to subtract the value of the next term from the accumulating value in result. So we've changed it so that we now check separately. If current is a plus, we'll match the plus. We'll call term. When it gives us back a value, we're going to add that value onto the result and then reassign result that new value. And similarly, if it's a minus, we'll match the minus. We'll call term, and then we'll subtract that value that term gives us back from the value in result and reassign that new value to result. And finally, once this loop is all finished and we've reached the end of the expression, we'll return the value that's in the variable result. Now what do we do with term? Here's the rule for term. It's a factor, possibly multiplied or divided by another factor, and then possibly another and another. So this is going to be a while loop. The lookahead that we calculated for this was H, you remember? So when we did H's lookahead, we got splat and slash as the two characters that current could be. So we're going to use those, and we're going to set term up very much like we did expression. These are the changes that we need to make to term. We have to change void to int because it's going to return a value. And don't forget to return that value right at the very end of term. When term calls factor, here and here, it's going to need to catch the value that factor returns. In this loop, it's going to either multiply that value that it gets back from factor times result, or divide result by the value that it gets back from factor. Let's go back a slide so that I can make this make sense. We're going to look at expressions while loop and remember what terms while loop looks like so we can compare. So in term, this while loop is going to say while current is the splat, the asterisk, or current is a slash. Then you separate out the two cases just as we've done here. If it's a splat, you're going to match the splat, and then when you call factor, you're going to multiply result times the value that factor gives you. Down here, you're going to be matching the slash, and then you're going to be dividing result by the value that factor gives you back. And at the very end of term, you're going to be returning the result. What about factor? factor doesn't have any of those meta-symbol Backus-Naur form things in it. So it's not going to change too much. The things she will change are that factor is now going to return a value, so don't forget to change void to int. And then when it calls either number or expression, it needs to catch the values that come back. If it calls number, it needs to say result is assigned number. If it calls expression in the else part of the rule, then it needs to say result gets expression, so that it's catching the values that it gets back. And at the end, it needs to return that value that's in result. And don't forget, you still are going to have an else error for factor, because one of these two rules has to be used, or else there is an error in the input. Now, number at first glance might appear to be a big pain, because we've been picking off a number digit by digit. A number is at least one digit, but could be many. And we're not checking for a maximum number of digits. That's a little bit misleading, because the way we're going to end up doing this, there is going to be a maximum number of digits, because we're going to let C++ handle the reading of a number and the evaluating of a number for us. And there is a limit to what C++ can do. So I'm kind of sliding that gently under the covers here. If we tried to evaluate the number ourselves, it would be rather a pain. Suppose you got the number 253. You'd get the 2, and then when you saw that there was a second digit of 5, you'd have to multiply that 2 times 10 to get 20, and then add on the 5, and at that point you'd have 25. Then when you read the 3, you'd have to multiply that 25 by 10 to get 250, and then add on the 3, and you would keep doing that for as many digits as you had. But we're going to actually simplify and let C++ help us. We're going to let it evaluate our number for us. The reason we're really going to do that is because we're going to change to real numbers. We're not going to be doing ints after all. I've been saying int all along, but I'm going to change it to double. You're going to change yours to double. That way your calculator will just be better. You'll have the option of dealing with real numbers instead of just integers. And it's an easy change. And so that's what we're going to do. We're going to let the system handle it for us. Let's see how. In C++, when you read a number, this is how you do it. You say cin, which is the name of your input stream, and then this operator. Remember, cout's operator pointed the other direction. Cin's points toward the variable. This needs to be declared of the type that you want C++ to convert for you. And so if this is an integer, it's going to pick up the digits and turn it into an integer. If it's a real number, it's going to do the same thing for a real number. Now, when a program has this kind of thing in it, what happens at runtime is it causes the program to pause. And usually you just printed a prompt to the screen. So the prompt would say something like, user enter a number. And then you'd hit this and the program would pause until the user presses enter. Now hopefully the user types some numbers before he presses enter. And if so, what happens when the program begins to run again is that the system will begin to pick off integer parts or real number parts until it hits a character that cannot be part of a real number, such as the new line character, and then whatever value it accumulated will be placed into this variable and the program will just keep on running. But now the only problem we have is that when we realize that we have a number, the way we realize that is that we've already read the first digit of that number. So if we now tell the system to accumulate a number for us, it's going to get everything except the first digit. We have to put that first digit back. And C++ has a really nice feature that allows you to put a character back into the input stream. So that's what we're going to do. We're going to put the first digit back and then let the system read the number for us. And then we have to read one more character to reestablish our lookahead and go back to things the way they were. Here's the code for the function called number. The way it is right now, it says it's going to return an int. Remember, we're going to change that. So we declare ourselves a variable to hold the integer that the system reads for us. This puts the single character of Lookahead that we have right now back into the input stream. All that really does is back up the little pointer that is in the buffer where the input is housed up backward one character. So that's all it does. It just moves that little locator back one character. Then this reads the integer and puts the evaluated result into this variable. This reestablishes our lookahead, so we get a character into current again. It'll be the character right after the end of the number, and then we just return the value that the system picked up for us. So it's really easy. Now, let's summarize. The functions you're going to need to write are main, match and error, expression, term, factor, and number. You will not have f or g or h or I. You will not have AddOp or MULOP. Your match and error functions will not change at all. We've just seen how expression, term, factor, and number are going to change, except for one thing. Instead of declaring everything as integers, make them all doubles. That's the only thing you're going to have to change. Change the return types of your functions and change the type of this variable that you put in every one of your functions to catch the results. Just make them all be doubles and everything will work fine for real numbers. C++ will let you type things like this if you tell it to pick up a real number, and it will do just fine with that. So if you are testing your calculator and you type something like 2.2 E, and that could be a capital E or little case, doesn't matter, and then a number of places, either plus or minus, this would be 2.2 times 10 to the minus third power, which is the same as this 0.0022. You can type things like this, and C++ will just deal with it. So you're going to have a very nice little calculator once you get this finished. Now, how do you have to change main? You don't have to do too much, but when you call expression, you do need to catch the result that it gives you back. So you're going to declare yourself a double variable in main called result and use it right here. When you call expression, just catch what it gives you back. And then when you check to be sure that you have a new line character in current, instead of just saying that expression was good or that was a correct expression or whatever it was you said before, print out the value of result. So you'll say something like expression evaluates to, and leave a little space right there so that your number is not bumped right up against the word to. And then you put the number, and then you put a new line character. Remember, you have to separate all your little pieces with these operators. And the same thing, if current is not a new line, then something happened and there's a bad error, or there's a syntax error in your expression. So this doesn't change. This is just like it was before. And then at the end of main, you should say return 0, just because that's a good practice for a C++ programmer.